I'm Alex Saroyan. I'm the CEO and co-founder at Netris. I'm presenting at Networking Field Day 40, and my presentation is about network automation, abstraction, and multi-tenancy. We call this NAAM. It's for AI factory operators for neoclouds, and this session is to help network engineers evaluate solutions and designs and architectures when they are building neoclouds and AI factories. And part 3 of this presentation is about consumption model. So these networks that we all are building, they exist for a reason. Someone is to consume these networks. And that someone can be the cloud operator, or that someone can be a compute orchestration product that's talking to network controller over API. And look, cloud been around for a while, and kind of over time, 10, 15 years ago, cloud introduced some abstraction model, VPCs, subnets, VPC peering, elastic IPs, elastic load balancers, and kind of time proved that it's a very useful model. Now this AI cloud operators, people on consumption side, not network engineers. Network engineers need to do their job, yes, but part of network engineers' job is to enable the consumption. And consumers don't want to consume switch ports or VLANs or VXLANs. They don't want that, especially given that average GPU server has like between 10 to like 40 connections. Really difficult for a consumer to manage stuff like that. So we're using a model that is very similar to cloud networking abstraction, VPCs and endpoints and things like that. So this is so I'm using this diagramming method here, where from one side we have this VPCs as a cloud construct. When someone is using the cloud, they don't see all the switches around it, but they do exist. And as a network engineer, you are responsible for that switches. While your consumer is responsible for consumption, you are still responsible for that switches. So the very, very basic concept here is the VPC, right? So VPC is what defines the isolation. And so basically, consumer wants to have the ability to say, hey, network controller, let's create VPC1, VPC alpha, and let's have this bunch of servers isolated in that VPC. So they want to have this ability to create very, very simple requests. Now, what you're seeing here, it's a screenshot from our web interface, and obviously everything can be accessed also through REST API, which is like how it's usually done, or through Terraform. We understand Terraform language, but this is just kind of visual example to keep all of us on the same page. Now, this is how you create. This is how you tell the system, hey, I want these two hosts, these two GPU servers, to be isolated together. I'm going to give this to my first tenant. Let's create a VPC and put these two servers in that VPC. Now, what needs to happen underneath, the system knows what your topology is like, what your Ethernet is like, what your backend Ethernet is like. Rocky and front-end Ethernet you configure differently. The way you configure VXLANs, in some place you use layer 3 VXLANs, in some place you use layer 2 VXLANs. Maybe you're using InfiniBand, but all that is not consumers' business. They don't care. And your network automation needs to take care of that. So what happens? All these algorithms know what exactly to configure in front-end fabric, back-end fabric, and your rack scale MVL fabrics. And then in some time, this isolation is enforced, and now these two servers that belong to Alpha can talk to each other, but like this other server that belongs to Bravo cannot talk to each other. So VPCs are an isolation. Obviously, in Ethernet, this achieved by using VRFs and usually L2 VXLANs. L3 VXLANs are also supported. Using partition keys and GUIDs if it's InfiniBand, and using GPU partitioning if it's MVL. I'm actually going to show how MVL works in a demo soon. So VPC is this like very, very kind of foundational construct. And then there is this other construct we call VNet. AWS calls this segment. Essentially, AWS calls this subnet. And VNet is basically Netris term for universal segment. It can be layer 2 segment, can be layer 3, can be VXLAN, can be VLAN. It can have a default gateway or doesn't have to have a default gateway. So it's a network engineering construct. So back in the day, when we all were working in data center networking, there was no VNet. VNet was happening between my compute, my Linux administrator colleague, and me. He would come to me and say, hey, Alex, we're deploying this new 5 servers for storage or whatever. Could you carve out a new VLAN and some switch ports and give me some IP addresses? That was the VNet. Today, it's a construct in a self-service portal, which is important construct when you are building a cloud, because these things, you still need to service that colleague, but now you need to service them programmatically and across different fabrics, not just Ethernet, but also InfiniBand and these other fabrics. So that's the idea of VNet. And the VNets can be created individually, one by one, or when you are doing this thing, so this thing is basically an object with 2 servers. You can tell Netris, you can create templates inside Netris, and you can say when my user is creating this kind of subcluster, I want Netris to create these 5 different VNets automatically behind the scenes. So this is mechanism that kind of connects network engineering world with AI cloud operator world. And that's in hands of network engineers. Network engineers define this translation. So VNet and VPC are this kind of very important constructs. And when you configure VPC becomes a VRF from Ethernet perspective. And when you configure a VNet, you basically turn certain switches into VTEPs. Now, obviously, Netris's algorithm knows which servers are connected to which switches, and we do not go and like replicate all these VRFs and VTEPs. No, we only configure VTEPs and VRFs where applicable. We take care of your TCAM and we don't waste your TCAM. It's bad. Wasting TCAM is bad. These GPUs are all big, but TCAM is still limited. Same technology, just more throughput, but same technology. And now, what if running a VTEP on a switch is not enough? What if you want to split a server? Because listen, when VTEP is on your switch, when you enforce this tenancy and VXLANs on the switch port, which is very important use case, your smallest unit of isolation is 1 server, right? Your tenant has access to server, but not to your switch. So switch is this safe place where you can enforce their isolation. But what if this cloud that you are building, this neocloud you're designing, needs to provide also granular multi-tenancy, splitting a host, virtualization. And you don't want to do this virtualization through using VLANs and sub-interfaces. You can do that. We do support that. But that is not as performant as GPU operators want. And if you're designing for lots of inferencing traffic, there is this thing called KV cache. It is very bandwidth intensive use of north-south interface, a lot of traffic exchange between GPUs and storage. And you don't want to use VLAN sub-interfaces for this. You want to use DPU accelerated isolation. So so that VLAN or VXLAN subinterfacing has to happen on DPU level. Now, so we came to sort of intricacies of host networking. What are some networking things that needs to happen on the GPU host itself? So one very simple thing, and these things are kind of optional. We have some tools here. Some clusters need these tools, some clusters don't. But my job here is to explain what is for what, and like if you're designing a cluster for AI, you'll know which to use, or you'll know what exists out there, and maybe you'll reach out and like we'll help you further. Anyways, host networking. This is your server, the GPU server. It has two interfaces, ETH0, ETH1, looking into north-south front end. And this is no DPU yet. DPU is running in NIC mode. Hardware is there, but DPU pretends it's a regular NIC. So 2 NICs looking into north-south. And 8 NICs looking into east-west, or your backend. Basically, 1 NIC aligned with each GPU. So they are physically connected, and traffic is not going through the CPU, but traffic entering this NIC is directly going into the GPU. NVIDIA calls this technology GPU direct. It's like RDMA level technology where like NIC talks directly, can write directly into memory of the GPU. This is important for Rocky. So your north-south fabric, your east-west fabric, backend fabric is running Rocky, which requires certain configuration on the switches, which is in Netris is one checkbox. You enable that, and algorithm knows, oh, okay, it's Rocky fabric, okay, we'll configure it differently. And now your switches act the Rocky way. But you also need to configure IP addresses and certain routes certain way on host side. And sometimes it's 8 interfaces, sometimes it's 16 interfaces. Sometimes you want to write a script to do this. Sometimes you want to use vendor's plugin to do this. We have a plugin, very optional. What it does, the nuance here is your host cannot have access to your network controller. This is your tenant's machine. Your tenant is has root access on the server. So this plugin needs to learn some information from that only your network controller knows, but without getting access to network controller. So what we do, we have this optional functionality where you can expose some insensitive information over LLDP. So your switch can signal the server over LLDP sending custom TLVs that this cable, this rail, should use this IP and this static route. So this is basically IP auto-configuration and routing protocol over LLDP that kind of custom created by us. Some customers use it. Some customers just use some custom scripts to configure that IPs. Yeah, we call that NHN, Netris Host Networking plugin for East-West. And then comes this other thing we call EOH, EVPN on host. Now, sometimes you have servers that are not DPU enabled, but they need to become part of your EVPN fabric. And you want to extend a VXLAN all the way into host. Why that might be the case? So imagine you're building a larger cluster. You want to support thousands of tenants. And you cannot use VLAN subinterfaces because there's no enough VLANs. You want to go beyond limits of VLAN. So what you can use is VXLANs. But how do I make my server, my host, to kind of understand VLANs? How to make it part of control plane? So we have this plugin you install on the server, and it will create bridge interfaces on the server, and these bridge interfaces will be endpoints in Netris. And you can say this virtual bridge endpoint and that switch port, physical switch port, should be together in the same VXLAN. The typical use case for this is when you have some servers for like control plane of Kubernetes or control plane of something that you manage for your customer, your tenant, but it's not the GPU host itself. Because GPU host has a DPU. If you want to do that granular multi-tenancy, if you want to do that extension of VXLAN into server on a GPU host, you just enable DPU and you do what I just explained in a hardware accelerated way. So how we help here, we have auto configuration of HBN. NVIDIA calls this HBN, host-based networking. The idea here is that the DPU and leaf switch, they form EVPN, BGP adjacencies and start exchanging EVPN routes. And that way, the host stops seeing your regular NICs. These two NICs that were previously visible to the host, they disappear. Instead, DPU shows up some additional kind of simulated NICs, but they are hardware accelerated. You can push like 400 gigabits of traffic through this so-called virtual NICs. And you can have many of those. You decide how many, like 8, 16, whatever. And then you can connect this, they are called VFs, virtual functions. You can connect these VFs to your virtual machines, to your containers, and now you have different containers or different VMs connected to a hardware accelerated sub-interface, which is first-class citizen in Netris controller. Then you can say, this VF and that switch port, they should talk to each other, and that will be 100% hardware accelerated at wire speed. Now, there's a method of doing this DPU overlay thing, okay way, and there's a method of doing this really, really right. Now, sometimes there's this misconception of like, hey, these DPUs are like switches. Let's run BGP adjacencies between DPUs, but not within the switch fabric, and let's run like an overlay between DPUs. Using the switch fabric as pure transport. Well, technically that works, but it leads to some problems, such as, in that case, only DPU-enabled endpoints can be your VTAPs. You can create a VXLAN between any DPU-enabled servers, but what if you have non-DPU-enabled servers on the cluster? What if you have a cable coming from another data center and your tenant needs to read a lot of data, which is very common use case? What if you need to connect your edge gateway to provide netting or load balancing functionalities? So this approach of disconnected DPU overlay it's a problematic approach. We do not recommend doing this because it leads to like workarounds after workarounds and after workarounds, and that does not scale. So the way we recommend doing this, and what is our default way of doing this, is what we call complete BGP EVPN integration, meaning that your switches, they all talk to each other EVPN BGP, as well as they talk EVPN BGP to your DPUs, meaning DPUs and every switch in North-South fabric, they exchange EVPN routes. And this means that you can create hybrid VTAPs. So basically, a DPU can become a VTAP for one service, and switch port can become a VTAP for another service. Make sense so far, this part? So that way you can, yeah?
So the VTAP on the server is doing my NCAP and DCAP for the tunnel?
On the DPU, yeah.
On the DPU, okay. So we're not doing it on the leaf.
Doing both.
Doing both.
Both. DPU on the server has its control plane shared with the leaf. So any route that DPU learns, your switches learn that route too, that prefix. So that allows you to create a VXLAN that has combination of switch ports and DPU virtual functions. So you can combine a virtual machine and a bare metal machine together. Like in this example, see, there's a server in VPC Bravo that is running in a NIC mode. There's no DPU, but it can become in the same VPC together with a DPU enabled host. I have more examples coming soon that kind of gives more use cases for this. So in this section, we are talking about how we deliver this consumption model to our cloud operators, cloud consumers. And a common question is, how do we as a neocloud, you're building, let's say you're building neocloud or AI factory, how you organize shared services? And a common example is storage. We have some storage system. How do we, we have our, different tenants, tenant alpha and tenant bravo want to have access to storage, but they should not be able to access each other, should stay isolated. So storage is usually, a group of servers. You put them into an isolated tenant, so storage machines need to talk to each other, synchronize data, whatever, and how to make other VPCs consume the storage. So we have this construct we call VPC peering. Our job here is to help network engineers deliver that cloud consumption model, so their AI cluster can be consumed as a cloud from network perspective. And the construct that helps here is VPC peering. It's a simple construct where you say VPC A should have access to VPC B. It's kind of easy for consumer to set this up. And from, like in this diagram, this bottom part kind of shows the logical, what is logically configured, and top part is showing what is actually being auto-configured on the switches. So in this case, alpha has VPC peering with storage, Bravo has VPC peering with storage, and on the switches, our algorithm will automatically configure VRF leaking. So VRF4, which is VRF for storage, will receive routes towards Bravo and Alpha, but Alpha will not be able to access Bravo, or Bravo will not be able to access Alpha, because if traffic leaving Alpha, entering that VXLAN of alphas, trying to get to Bravo's IP addresses will not be routed, because that VRF has no idea how to route. So ASIC will never route that traffic. So it's safe. It's easy to implement, easy to consume, easy for you as a network engineer to implement when you have a tool that does this, and it does the job. And this also works if you have a kind of mix of DPU-enabled hosts and non-DPU-enabled hosts, because we always combine control planes of DPUs with leaf switches, and so like switch or DPU, we kind of treat them the same. There's this example of direct connect. So what happens if your tenant has some data located in some remote site, and they do a lot of data exchange? This AI is a very data-intensive business. So when you serve these AI tenants, you'll realize that they are exchanging a lot of, so like your tenant willing to send and receive few terabits of data out and in and out of your data center. That's like a normal ask. And like how do we organize this? And let's say they have this remote site where they have a ton of data, and there's a cable coming from remote data center, and this is not one-time thing. This is not like, hey, we'll make it work and whatever. It's something you want to enable your cloud operators to be able to do this easily, programmatically. So to organize that, we have a construct. It's a BGP construct. It is used also for defining your uplinks when it comes to like connecting with your border router. But in this example, we are using a BGP connection for forming a BGP connection between the physical switch port and the VPC. So this is similar to what AWS calls AWS Direct Connect. When you have a VPC inside AWS and you have a cable, coming from AWS to your data center, you can configure a BGP on your router between your router and your VPC, right? Now in this example, you are the AWS. You are building AWS. How do you provide similar service to your customer? So this is how. This construct allows doing that. It's the same construct you use for configuring your upstream connections between your leaf-spine fabric and your border routers, with the only difference that in that case you would configure this BGP session between your border router and your infrastructure VPC, your network engineering VPC. But in this case, you are configuring this for the VPC of your customer. So we have this kind of knowledge in our cloud construct model, where you can say this BGP doesn't go to the main VRF, but it goes into my kind of customer-specific VPC. Okay, one more thing. So we talked about how we configure lots of things across switches, high performance data, terabits of traffic between storage, GPUs, and how we isolate all that on a hardware level. And then there's still one missing question. How do we provide connectivity between VPCs and internet? So AWS, again, to use this analogy, AWS has these functionalities they call elastic IP, which is a construct that allows to map one public IP with one private IP, and elastic load balancer, which is basically mapping one public IP with a group of private IPs. And if you, as a network engineer, as an architect, you are building AWS, again, you need to be able to provide this functionality to your tenants. And to help with that, we have built this technology we call Netris SoftGate, and it evolved since last time we presented here. So now Netris SoftGate is horizontally scalable, and it's multi-tenant. What functions it provides? Look, it provides three basic functions: NATing, layer 4 load balancing, and DHCP. You might say, not like DHCP, NATing, load balancing. It's not rocket science. The challenge with this is that when you try to deliver these very basic functions in a multi-tenant and horizontally scalable way, that is very difficult. Most devices that are designed to provide NATing and load balancing or DHCP, they are designed for data center use case. So you can have like big, powerful devices, two of them, working in HA cluster, but most of them are not horizontally scalable. They are not designed for cloud provider use case. And they are not multi-tenant in a sense. Yes, you can configure VRFs there, but how SoftGate is different from multi-tenancy perspective, it fully integrates with your front-end fabric. It becomes part of the fabric. Switches think that SoftGate is another thing, versus SoftGate in reality is a server. You dedicate some servers for this function. And if we look under the hood of AWS, they do something very similar. They have their own proprietary accelerated software gateway for these functions. And we realized that if that approach works at AWS scale, maybe anyone who's building AI clusters in getting closer to AWS scale, they will need this technology. And we created this technology, which is XDP accelerated software. So you dedicate several servers. They connect to your leaf switches. They form EVPN, BGP adjacencies. That way, this cluster of SoftGates can tap into every VRF and into every VPC, obviously according to your instructions. And it can scale horizontally. So you start with 2, or you need 4. 4 is the minimum. You start with 4, and then as you monitor utilization of CPUs and RAM, and you add more SoftGates, and it will automatically rebalance the traffic. Now, delivering these functions, NAT, layer 4, LB, and DHCP in a multi-tenant and horizontally scalable way is really, really, really difficult. This is why SoftGate exists. And look how it works. So from a consumer perspective, from network engineer perspective, you just deploy several SoftGates, and these are your kind of data planes. And then consumer starts creating load balancers, which is, can be TCP, can be UDP, it is VPC aware. They pick some front-end IPs from a pool that you define. They can do some health checks. Very importantly, we have our proprietary implementation of maglev algorithm. This is very important when you are building scalable systems, because think about it. What if, like these SoftGates, they don't share state? You're not allowed to share state. When you're building cloud scale something, you cannot share state. It doesn't scale. And it becomes very challenging. So we implement maglev algorithm that helps us with layer 4 load balancers, like different SoftGates, unaware of each other, are load balancing same traffic for destined to different servers, and they all end up with the same consistent load balancing. There's additional things that we do to make sure that NATing works correctly. Again, a lot of math and a lot of kind of creative algorithms involved that we implemented on low level using XDP and C programming to deliver the right performance. This is example of how you configure NATing. So this is VPC aware NAT. You can select your VPC, you pick your public IP address, you pick your private IP, and then traffic coming from the internet passes through your fabric. So this red line is load balancer traffic. It's coming from the internet. SoftGate is like a router on the stick. It's connected to a few leaf switches. It's not connected to your border router directly. It's connected to border router indirectly. So the traffic physically passes through the fabric. It comes into a SoftGate. SoftGate decapsulates this traffic, and SoftGate knows, oh, okay, this traffic belongs to VPC alpha. And if alpha and Bravo have overlapping IPs, that is fine. SoftGate knows how to handle that. And then it uses maglev algorithm to decide whether this packet goes to server 1 or server 2, and then checks health checks, and then sends to right, encapsulates with right VXLAN and sends further into fabric. Similarly to that, NAT flows work. They arrive at SoftGate, and destination IP or source IP is changed, and then NATing happens.
Quick question for you, Alec. Where does, I'm sorry if you covered this, where does the SoftGate live?
You dedicate several servers for this function and connect to some leaf switches.
Okay.
Usually you would connect to border leaf, but doesn't have to be there. Like any switch is fine.
Okay. And what is it a container, VM, any of the above?
No, it's the whole server. Oh, it's not containerized.
Bare metal server.
Bare metal server.
Got it.
So multi-tenancy is not implemented through running different VMs. That's not performant. The data plane that we developed, it's low level, like XDP, like literally in like low level C++ code.
Got it.
That data plane is able to deal with overlapping IPs, and it understands VPCs. This is what makes it performant. Using a bunch of open source components and containers, that will work for a lab, but that will not be performant. We've tried that. You want cloud scale performance, you need to deal with low level development.
Thank you.
And then with providing all this access between VPCs, between internet, between direct connect, with all these things, maybe you're asking, okay, how do we control traffic? Maybe when I let my tenants to access my storage, maybe I don't want them to be able to SSH to the storage. Maybe I want them to access certain ports, right? So yes, obviously there's a construct for providing VPC-aware ACLs, which is on consumption side. It's a simple construct where you say, this is my VPC, this is my source IP, destination IP, these ports I want to permit or deny. And what algorithm does, see, we're talking about hundreds or thousands of switches and lots of DPUs, and where to insert these rules. If algorithm inserts these rules everywhere, just in case, we're gonna run out of TCAM very, very quickly. So we're not doing that. The algorithm is smart enough to continuously on the fly analyze your routing tables in each VPC and dynamically inserts all these rules in the right places. So if you have ACL that is, let's say, is trying to permit or deny traffic coming from the internet through SoftGate behind elastic IP, for example, that enforcement will happen on the place that is closest to the entry point, on the SoftGate itself. But when you are trying to access control traffic that's going between two kind of switch terminated endpoints, let's say between storage and servers in the VPC alpha, then you want this enforcement to happen on switches in the hardware and not degrade your performance. So in this case, we automatically apply this on switches using TCAM. That's the only way. And if you have DPU accelerated servers connected to the same leaf switch, the algorithm is kind of smart enough to not apply these ACLs on the switch, but apply on the DPU. That way we save TCAM usage. We reduce TCAM usage that way. So where possible, we would push away these ACLs to minimize TCAM usage. Where not possible, we'll use TCAM. So I walked you through what we call bare necessities for building network automation for large-scale AI clusters. We call this NAAM, Network Automation, Abstraction, and Multi-tenancy. We created a checklist of all these things, of bare necessities. So there's a link. You can go through that link, put your email and information, and then we will send a checklist. And this checklist will help you kind of go through what are the bare necessities for building AI cluster network automation. And if you ever have questions or have interest in the product, please reach out to our sales team. They will connect you with solutions architects. We'll provide access to Cloud SIEM so you can try the technology. They will help you to figure out whether this technology is right for you or not, and will help with throughout your AI infrastructure networking journey.